Right now, everything you send is scrambled. Your messages, your passwords, your money, all of it, turned into nonsense that only the right person can read. But here is the question that has haunted people for thousands of years. Can a secret ever be made truly unbreakable? And that opens a flood of questions. Who first tried to hide a message? Why did every code that seemed unbreakable eventually fall? And how on earth do two strangers agree on a secret in the open, where everyone is listening? What is actually happening behind the little padlock in your browser? Is anything provably safe? And is there a machine coming that could shatter all of it, overnight? We will answer every one of these questions, and more, in this video. But to really understand it, we have to go back, all the way to the beginning. Because the encryption protecting your entire life did not appear overnight. It is the end of a 2,000-year war between codemakers and codebreakers. A war that starts not with computers, but with a simple trick used by a Roman general to hide his orders. And one impossible dream. The dream of a message that no enemy, no genius, and no machine could ever crack. So let's find out whether that dream is real or whether every secret is living on borrowed time. 2,000 years ago, Julius Caesar had a problem. His messengers could be captured, so he used a trick shift. Every letter in the alphabet forward by 3. A becomes D, B becomes E. The message turns to gibberish. To read it, you just shift back by 3. The secret? The thing you must not reveal is only the number 3. This is the entire idea of encryption, a method everyone knows, and a key that only you know. But a shift of 3 is easy to guess, so people upgraded it. Instead of shifting, scramble the whole alphabet map, every letter to a random other one. Now there are more possible keys than grains of sand on Earth. Surely that is unbreakable. For centuries, people believed it was. Then Arab scholars discovered a devastating weakness, and it had nothing to do with trying every key. Every language has a fingerprint. In English, the letter E shows up far more than any other. So in the scrambled message, whatever symbol appears most often is probably E. Match the frequencies and the code unravels itself. The and letter patterns fall into place. No guessing every key, just counting. The unbreakable cipher was broken by simple arithmetic. The lesson was clear. A clever scramble is not enough. To truly hide a message, you needed something that changed the code with every single letter. And that would take a machine. This is the Enigma machine. In the 1930s, Germany believed it produced codes that were, for all practical purposes, unbreakable. And you can see why. Look at it. This is not a scramble on paper. It is a scramble that rebuilds itself with every keystroke. Press a letter, and an electric current races through 3 spinning rotors, bouncing back and forth before lighting up a completely different letter. That is your encrypted output. But here is the genius. The instant you press a key, a rotor clicks forward. So if you type the letter A 3 times in a row, you get 3 different letters out. The frequency fingerprint, the trick that broke every code before, is gone. With the rotor positions their order and a plugboard swapping letters on top, the number of possible settings was astronomical. Over 150 million combinations, and they reset it every single day. Cracking it seemed hopeless. But at a secret site in Britain called Bletchley Park, a team led by Alan Turing built a machine of their own to fight back. This is the bomb. Turing realized they did not need to try everything. The Germans were predictable. Messages often contained the same words, like a daily weather report. By assuming a word was hidden inside, the bomba could rule out billions of settings at once and find the right one. The unbreakable machine had been broken, not by brute force, but by human habit. And it revealed a deeper truth. As long as a code follows any pattern at all, a clever enough enemy can find a way in. Which raises a wild question. Is there any cipher that is provably, mathematically, impossible to break? There is exactly one cipher that is mathematically, provably unbreakable. It has been proven, no computer, no genius, no amount of time can ever crack it. And the idea is almost insultingly simple. You take your message, then you take a key that is completely random, and exactly as long as the message, you combine each letter of the message with one letter of the random key. That is the whole method. Now watch why it is perfect. An attacker who tries every possible key does not get one answer. They get every answer. The ciphertext could decode to attack at dawn, or retreat at noon, or buy more milk. Every message of that length is equally possible. The encrypted message contains literally zero information about the original. There is nothing to analyze, no pattern to find, no fingerprint. It is not just hard to break. There is nothing there to break. So why is your phone not using this right now? Because the perfect cipher has 3 brutal catches. The key must be as long as the entire message. It must be perfectly random, and you can only ever use it once. But the worst problem is this. To send a secret message, you first have to secretly deliver a key that is just as big as the message. If you had a safe way to deliver that key, you could have just delivered the message the same way. And there it is. The problem that trapped cryptography for 2,000 years. To share a secret safely, you first need to share a secret safely. It seemed like an unbreakable circle until 1976. Here is the puzzle that mattered more than any cipher. Imagine you want to send a secret to a stranger on the other side of the world. Every message between you passes through wires you do not control, and someone is listening to all of it. This eavesdropper hears every word you both say, so you cannot just send them the key. The moment you do, the listener has it too. And you have never met, so you could not agree on a secret in advance. For centuries, everyone assumed this was simply impossible. To talk in secret, you must first meet in secret, or trust a courier. There was no known way for 2 strangers to create a shared secret while a spy watched every exchange. But what if you never send the key at all? What if instead the 2 of you could build the same secret, separately, out in the open, using something the eavesdropper cannot reverse? Think of it with paint. You and the stranger agree, publicly, on a starting color. Then each of you secretly adds your own private color and mixes. You swap your mixtures out in the open. Now, you add your private color to their mixture, and they add theirs to yours. Because mixing order does not matter, you both end up with the exact same final color, but the eavesdropper, who only saw the mixtures, cannot unmix them to find your private colors. A shared secret built in plain sight that a listener cannot recreate. For 2,000 years, this was a fantasy. In 1976, 2 researchers turned that paint analogy into real mathematics. This is the paper that changed everything. New Directions in Cryptography, 1976, by Whitfield Diffie and Martin Hellman. It opens by declaring that cryptography is standing at the edge of a revolution. They were right. Their claim, right here in the abstract, sounded impossible. 2 people could establish a shared secret key over a completely insecure channel. No prior meeting, no trusted courier. Even with an eavesdropper watching every message. Their trick was the paint mixing idea, but built from numbers. Everyone agrees on a public starting number. Each person picks a private secret number and combines it with the public one, using a special kind of math. The magic ingredient is a one-way function, a calculation that is easy to do forwards, but practically impossible to undo. You can mix the paint, you cannot unmix it. In their math, that meant multiplying was easy, but working backwards was hopelessly hard. So the 2 strangers swap their combined numbers in the open. The eavesdropper sees both. But to find the actual secret, the listener would have to reverse that one-way function, and that could take longer than the age of the universe. Meanwhile, each person finishes the calculation with their own private number and lands on the exact same secret key. 2 strangers, who never met, now share a secret, and the spy who saw everything has nothing. This was the birth of public key cryptography. It solved the 2,000-year-old problem in a single stroke. but it left one door open. What if you wanted to lock a message for someone before you had ever exchanged anything at all? 1 year later, 3 names answered that. In 1977, 3 researchers at MIT, Ron Rivest, Adi Shamir, and Leonard Adelman, turned the new idea into a system we still use today. It is named after their initials, RSA, and it introduced a beautiful concept, a pair of keys. Every person gets 2 keys, a public key, which you hand out to the entire world, and a private key, which you never ever share. The trick is that these keys are mathematical opposites. Think of the public key as an open padlock. You give copies to everyone. Anyone can put a message in a box and click your padlock shut. But once it is closed, only your private key, the one you kept, can open it again. And the whole thing rests on one piece of math, spelled out in this paper. Take 2 enormous prime numbers and multiply them. That is easy, but hand someone only the result and ask them to find the 2 primes you started with, and they are stuck for centuries. That is the one-way trapdoor, easy to walk through in one direction, practically impossible in reverse. Your public key is built from that giant product. Your private key is the secret of which primes made it. Everyone can lock. Only you can unlock. And it works in reverse too. If you lock something with your private key, anyone can check it with your public one. Since only you have that private key, it proves the message truly came from you. That is a digital signature. Encryption and proof of identity from the same idea. Diffie-Hellman and RSA quietly became the foundation of the entire internet. Every bank login, every private message, every online payment, and it is all hiding behind one tiny symbol you see every single day. The padlock. You have seen this a million times. The little padlock in your browser, most people think it just means safe. But behind that tiny icon, a lightning-fast handshake is happening, using everything we'd have learned in this video. When you connect to a website, your browser and the server run a handshake. First, the server sends a certificate. Think of it as an ID card, digitally signed by a trusted authority, proving the site really is who it claims to be. Your browser checks that signature using public key math, the RSA idea. If the signature is valid, you know you are really talking to your bank and not an imposter pretending to be it. This step stops attackers from faking a website. Next, your browser and the server perform a key exchange, exactly like Diffie and Hellman described. Out in the open, across the internet, they agree on a shared secret key that no eavesdropper can recreate. But here is a clever twist. That public key math is powerful, but slow, so it is used only to agree on the key. After that, both sides switch to fast, simple encryption, using that shared secret to scramble the actual data. Once the handshake finishes, everything you send is encrypted. Your passwords, your messages, your card number. The listener on the wire sees only meaningless noise. That entire dance happens in a fraction of a second every time you load a page. 2,000 years of code making and code breaking, all working together, behind one icon. It feels like the war is finally won, but there is a shadow on the horizon, and it has been waiting since 1994. Remember the one thing that keeps RSA safe, that factoring a huge number back into its 2 primes is practically impossible. In 1994, a mathematician named Peter Shor wrote this paper and quietly detonated that assumption. Shor proved that a quantum computer, a fundamentally different kind of machine, could factor enormous numbers, not in centuries, but in hours. The one-way trapdoor that protects the internet would suddenly swing open in both directions. A normal computer, cracking a key, has to try possibilities, more or less, one at a time. A quantum computer exploits the strange physics of the very small to explore a vast number of paths at once. For most problems that does not help, but for factoring, it is devastating. Now, the honest catch, nobody has yet built a quantum computer anywhere near powerful enough to break real encryption. The machines are fragile, error-prone, and tiny. It could be 10 years away. It could be 30, or it could stall forever. But there is a chilling twist. An attacker does not have to wait. They can record your encrypted secrets today, store them, and simply wait for a quantum computer to arrive. Harvest now, decrypt later. Some secrets need to stay hidden for decades. So the world is not waiting either. Cryptographers are racing to build new algorithms based on math. Even a quantum computer cannot easily undo. This is called post-quantum cryptography, and it is already being rolled out quietly right now. And so the oldest war in history rolls on. Every unbreakable code, from Caesar to Enigma to RSA, was eventually broken, or is under threat. Each time, we built something stronger. Each time, someone found a new crack. So, can a secret be truly unbreakable? On paper? Yes, just once. With a perfect key in the real world, every secret is only safe until someone gets clever enough. The padlock is holding, for now. Like and subscribe for more.